working? It might be. Let me check. I don't really know how to know if it's working. Is it? It's not showing up there. It has a little red button though, so you know, that's a good sign. Okay. Is it working? I can't really tell if it's working yet. Let me see. It is! It looks like it's working! Finally! That took like a long time. I think it's echoing because I have my sound on. So I'm just going to put it on mute and hopefully you guys can hear it. Can you hear it? Can you still hear me? I don't really know. This thing is a pain. And now it's like it's showing me and strange. Oh, this is weird. Let me turn it this way. Let me pause it. I don't really know if you guys can hear me. I hope you can. Why is it just showing me on my phone? Why is it still filming this? This is so frustrating. I think it's working though. Hopefully. I don't know why it looks like this. So, let me just try one thing real quick. It says one person's watching, so it must be working if they can watch it, right? I also don't know why it's so squished. Also, it's really delayed and it's annoying. I turned off the sound so that way I wouldn't have to hear my own voice, and it's delayed, so it's repeating over me. But anyways, let me get started and just hope... Oh, never mind. It went down to 0 watching. Oh, it's Emily. Oh, very nice. Is it working? I feel like half of this is just going to be me asking, can you hear me? Like, is it working? Does it work? Can you hear me? Oh, okay, good. She can hear me. Oh, okay. So I guess I'll get started then. Emily sent me a bunch of questions, which I'm going to start out with. So we're going to start off with kinematics. And first of all, we're just going to go over the variables because someone else asked for that too, so let me just move that. Okay. So while I'm doing this anyways, oh yeah, someone else can see it. Okay, that's good, as long as people can see it. So let me start with the variables. So we have vi, initial velocity, vf, final velocity, delta t, change in time, delta x, change in position, and a, acceleration. These are our main kinematic variables. We're going to be using them quite a bit. And I think people want me to go over kind of just what they mean, because some people miss them in the beginning, and then it kind of messes them up for the rest of the time. Oh, someone else. Oh, Chris can see and hear me. Okay, that's good. I'm going to put this on Do Not Disturb so it doesn't keep interrupting us. Okay, well, initial velocity, that's your velocity at the beginning of something. Like when you're just starting the problem, that's your velocity. And as a refresher, velocity is speed and direction. So it can be negative final velocity, your velocity at the end of the problem. Delta t, time elapsed, so the time from the beginning of from the end of the problem. Delta x, the distance, well, the displacement, so your final position minus your initial position, and acceleration, your change in velocity. So some people are confused about the kinematics equations themselves because it's a bit tricky because on our sheet they're written different than they are in, where did I have, here it is, than they are like when we're taught in our notes. Like here I've got them as we were taught in class. So in class they look like this. Final velocity is equivalent to initial velocity plus acceleration times delta t. Delta x is equivalent to initial velocity times delta t plus 1/2 acceleration delta t squared. Final velocity squared is equivalent to initial velocity squared plus 2 times the acceleration times delta x. Delta x is equivalent to 1/2 initial velocity, well, inside parentheses, initial velocity plus final velocity times delta t. So these are our kinematics equations on here, and these are all constant acceleration. So I got all these new colors, so I'm going to use them. So we're going to use pink to write the names. So here are, oh, it's kind of thin. I don't know if you guys will be able to see it. Constant acceleration. I'm just going to put an A because I don't think I have room to write acceleration. And then we have our constant speed equation. So constant speed. And I have enough room to write speed, so I'll write that one out. And that is, this one is delta x, where is it? Delta x is equivalent to velocity times delta t. And see how this is Vx and it's not like Vi or Vf? That's because when you're in a constant speed equation, you're not accelerating, so your velocity is the same throughout the whole time, so your initial velocity is the same as your final velocity, so it's just Vx. Now, on the sheet, it's a bit tricky because they're written differently. This is the one that we have, but on our sheet, this, I'll use another color, because I have all these new colors. I have like 2 greens, 2 blues, 2 times. I also found these weird ones. They're like purple, but they don't work very well. It's a shame. Anyways, so on our sheet, delta t is just written as t. That one's pretty easy. Initial velocity is written as Vxo. I like this color. Final velocity is just written as Vx. Delta x usually is written as like, it's written as x and xo. And this is like final position and initial position, so you just have to subtract them, it's fine. So like, well, acceleration is a, usually with an x there. Anyways, but so like when you see an equation with the x's, like let's see, the second one on the sheet is x is equivalent to initial position plus initial velocity times time plus, this is really messy, xo plus 1/2 axt squared. Just ignore this first O, because this is actually, this equation here, that's really messy. I think it's because the angle out of that. Sorry about that. But yeah, this is this equation. Good? Good on kinematics equations? Let's see what's next on the list. Or if I have any more questions sent to me. Where's my eraser thing? Oh, here it is. I'm also filming on my laptop today, so it's really weird. Sorry. Usually I'm on a flip camera, but I don't think I could live stream from that, so oh well. Next is conservative, isolated, and closed systems. What do these mean? Alright, so let's use a picture, because pictures are fun. We'll use this color. So we've got a guy on a skateboard ramp that goes like that. That's flat at the bottom. It doesn't go up. It looks like it does, but I made a mistake. So here he is at the top, and he's on his little skateboard. And here, well, this is a bad example. Let me use a different one. Also, this thing is kind of like dripping. I don't know if you can see it. Maybe these markers aren't that good. Isolated, conservative, and closed system. I'll use smokestacks instead because people don't get smokestacks either. So, you have your smokestacks. These are all the same height, even though they don't look it, just pretend that they are. So we're going to call this one total energy, total mechanical energy, gravitational potential energy, and kinetic energy. Now, just as a review, total mechanical energy is all the kinetic, gravitational, or spring potential energy in an equation. It doesn't include friction or thermal energy or something like that. So if we had something where at the start of our problem, problem, we had all of the energy. That looks like that. We had all the total mechanical energy, and let's say that it was just all in gravitational potential. So we'll say that there's like a guy standing, well, not standing, but like he's at the top of a hill. And we'll put him on a skateboard, because skateboards are key in physics. You'll see them all the time. So here's him at the start of the hill, and then let's put his energy when he reaches point B. So here he is at the bottom of the hill. So his total energy, and total energy includes friction. It includes everything, gravitational potential, kinetic, spring potential, and friction, all of the above. So here's his total energy. And let me just draw the other smokestacks. Here is his gravitational, total, mechanical, energy, and kinetic. Okay, so at the bottom, he is at the bottom, so he has no gravitational potential because he has no more height. We'll say that this line is equivalent to 0. So he's at 0, he's got no height, so he's not going to have any gravitational potential. Kinetic energy, he's actually going to be going pretty fast. He built up some speed going down this hill, and now he's got velocity. Except his total mechanical energy looks like this, and his kinetic energy looks like this. What happened here? Well, the thing is, this isn't a frictionless hill. He had friction going down the hill, so he lost some of the energy that he would have had to friction. So his total mechanical energy, which is the sum of, I guess I'll just make spring potential columns, just to make this easier to see, which is the sum of his gravitational, kinetic, and spring potential energy. Here, it dropped down. Why did that happen? Because there was friction, except the total energy is the same because the total energy includes the friction. So is this a conservative system? No, it is a non-conservative system because it's seen as like open, where like energy can escape through friction and heat and stuff like that. Whereas if this was a frictionless hill and he had the same total mechanical energy at the top and at the bottom where he didn't lose anything to friction, and it looked like that, then it would be a conservative system. Because it's closed, there is no energy escaping through heat or friction or anything like that. Hopefully that makes sense. If not, let me know and I'll try to go over it again. Here's my eraser. Let's see what's next on the thing. That's a terrible eraser. Well, it is just a paper towel, but still. Graphs. Okay, area, displacement, and slope of each type. All right, graphs. Graphs aren't too bad. Let's see. This stuff is stubborn. It doesn't come off very easily. Okay, so graphs, they can be really frustrating, but once you get the hang of them, it's not that bad. So let's use green again, because I like this color. So you have a position time graph. So we're going to put position on the y-axis, time on the x-axis. We're going to have a velocity time graph, velocity time, and an acceleration time graph, acceleration time. Now let's write in our variables, because this is going to help us later on. So position is going to be in meters, time is going to be in seconds, velocity is in meter per second, meters per second, not meters per second. Time is going to be in seconds, acceleration is going to be meters per second squared, and time is going to be in seconds. So let's say that we have, what's a good one? Well, we won't put anything in here yet. We'll just see how it works out, and then we'll put stuff in after. So on a position versus time graph, so we'll just call it and then on a velocity versus time graph, and on acceleration versus time graph. We're going to make a little table so we can see. What is the slope and what is the area? Oops, that's not how you spell area. Oh no. There we go. What is the slope and what is the area? Okay, we really just have to look at the values to find out what the slope and area would be. So slope, we know that it's rise over run, so it's the value, well, you just look at the measurements, so it's the measurement of the y-axis over the measurement of the x-axis. So in a position time graph, the slope is in meters per second. What else is measured in meters per second? Velocity. So we know that the slope has to be velocity. Does that make sense? I'll write rise over run, just in case. And then area, we know is, well, it's the rise times the run, I guess you could say that. It's usually not said that way, but you can say that. So in this case, this is meters times seconds, and we don't really have anything for that, so we're just going to put an x there, because we don't have, none of these variables have meters times second as their measurement. So then let's find the slope of a velocity time graph. Meters per second divided by second. Well, meters per second divided by second, well, I guess we'll just write it like that, ends up to be meters per second squared. Then we can just, so then we know that this, actually that x looks like it's that. I'm just going to scribble it out instead, that way we don't get messed up. So now we know meters per second. Acceleration is measured in meters per second, so we know that the slope of this is going to be acceleration. What about the area? Let's see. Well, if it is, where's my eraser? There it is. If it is meters per second times seconds, then it's going to look like this, right? We're just going to put a 1 there because there's nothing there, so it can be over 1. Well, then the seconds are going to cancel out, and then we're just left with meters. What's measured in meters? Positions. Then we can write position. And then let's look at acceleration. Well, meters per second squared divided by seconds isn't really anything, so we're just going to kind of block that out. But this thing is stubborn. Meters per second squared divided by seconds is equivalent to meters per second. What's measured in meters per second? Velocity. There we go. So now, do you see how you would get it from each of these? How you could find the other variables from these graphs? Hopefully that makes sense. Let me know if you want me to go more into detail on that. What's the next thing on the questions list? Did anyone text any questions they want to answer? Oh, I have a phone call from someone. What? Oh, no one can see what I'm drawing on the board. Oh, okay. Let me see. I should probably check these more often. Maybe I should turn the sound on. Can you? I'm trying to make it so that you can see it. 1 sec. Let me try something. What if... What if... No? Can you see blue? No. Oh dear. Green? No. What if... it again. I'm not sure if that worked. Let's see. Oh, Kaya wants to know if I can explain the difference between the energies. One sec. Before I do that, I'm just going to make sure someone can see it. Okay, let's see. Does it work now? I went and I found some other markers. That's good. They're not as fun or as colorful, and I changed the lights. I feel like this is too close up now. I feel like it's in my face. Is it gonna work? This live stream's a mess. I feel like half of it is just me asking if it's working. Does it work? I think so. Oh, my goodness. Did she reply? No. Oh well, I'm just gonna keep going anyways. Let me know if you want me to redo the last stuff with the board so you can actually see what I'm doing, or if just hearing it was good enough for you, because I can redo it if you want. Oh, she said it's yes. Okay. Oh, and Emily Johnson. She's so cute. So then, can you explain how to differ between the energies? Okay, so, Kaya wants me to draw on the board? Okay, I'll do that after, then the people who already saw it are fine with it. So, the difference between the energies. The main energies that we use are, this marker is dead. It's a good thing I got 2 black markers, because that was pretty bad. I have like 20 markers over there now. So, kinetic, gravitational potential. This one isn't great either, but at least you can see it. Kinetic, gravitational potential, spring potential, can you see that? Let me just check. One sec. Really quick. Just want to make sure. I think you can see it enough. I thought that I got a good black marker too, but I guess not. So kinetic energy, we use the symbol K, and its equation is 1/2 mass times velocity squared. Gravitational potential, we write as U. This is a terrible marker. Can you guys see red? Because maybe this one will work better. Can you see that? It's pretty dark. Oh, it's so laggy that I can't see if it works yet. One sec. Can you see that? Yes, you can. You can see that. You'll be fine. Alright. So then, K equals 1/2 mv squared. Gravitational potential we write as U subscript G, and it's equivalent to mass times gravity times height. There's like this big red splotch. Spring potential is US, and that one is equivalent to, I never remember this equation. Where's my sheet? Here it is. That is equivalent to US equals 1/2 kx squared. So first of all, let me explain what the variables are in these equations, because then you can understand the difference between them. K, well that's kinetic energy. 1/2 m mass velocity, v is velocity, mass is the m, gravity is the g, h is the height, or sometimes it's delta y, vertical displacement. Spring potential, K is the spring constant. That's going to be different. It's like really like kind of like how strong the spring is, like how much it'll fight back when you push it, kind of. I don't know if that's a good way to describe it or not. And then, why is this doing that? Anyways, but delta, well, this is sometimes written as delta x, but this is how far the spring is compressed. So what is the difference between these? Well, the easiest way is to just kind of look at something. So let's say that we have a guy on a skateboard, because you always need skateboards in physics. That's just how it works. Here's a guy, that looks more like a surfboard. There we go, now he has wheels, now it's a skateboard. Gravitational potential, we have a guy and he's skydiving. This one, he's got a parachute. Well, actually a parachute would introduce drag, so he's just skydiving, hasn't opened his parachute yet, so he's just falling. I'll just draw some lines behind him to show motion. And then spring potential, we've got like a block pressed up against a compressed spring. This is a wall. Actually, no, the ground has to be there, or else gravitational potential. So here's a block on a spring. So let's see what they have. This guy has velocity. Actually, this guy would need, this is annoying, 1 sec. So actually this guy's going to be standing on top of a cliff about to fall off. He's not skydiving anymore. He decided that that was a bad life choice. But now he's sitting on a cliff, so maybe he's just not that bright. Anyways, so this guy has velocity, and he's moving this way. This guy is really high up, and this guy is on a spring compressed against the wall. Well, you can see that this is kinetic energy because he has velocity. Which one of these equations has velocity? Kinetic energy. This guy, we know, has gravitational potential energy because he has height. And which one of these has height involved? This one. And we know that this one is spring potential energy because there's a spring. That's usually a good sign. If there's a spring, it's like a very good chance that it's spring potential energy. Let's see. Joe Durkin says, Sinead, do you have your old tests with you in case anyone wants to reference a specific question? Yes, I do. I have my folder. Oops, dropped my pencil case. Oh, I have my folder with my old tests in here in case anyone needs help with a question on that. Yeah, Kai, I do. Let's see. Any questions in the group chat? Red works. Good. Very good. I really feel like this entire thing is just me being like, oh, sorry, it doesn't work. Oh, Leo was asleep. So was Ayana. She just woke up. Oh, huh. Chris says that it works. Darker marker. Yes, yes. Okay, so Joe, if you have a specific question on the test, just let me know and I'll do that. Kaya, can you go over the free response from the test? All right. Let me erase all of this. The free response from the test. Do you mean the most recent one? That's my guess. You probably mean the most recent one. So, let's see. What was that? I'll erase this first. Filthy. I should really just like actually clean it one of these days, not just wipe the marker off. There we go. Almost. There we go. Good. Okay. Kai says literally all the tests. After you do the free response, can you do 18 from the chapter 3 test? Well, Kai, since you don't have a specific one, I'll just do 18 from the chapter 3 test. Let me just find it. One sec. Chapter 9, 10, not that one. Chapter 3, oh, chapter 3, that's the one we need. You say 18. All right. Oh wait, 18 isn't a free response. Oh, okay. Well, just let me know a normal, like, free response one, and I'll do it. Where is 18? Oh, okay. So, a cannon fires a cannonball horizontally at an initial speed of 10 meters per second from a height of 45 meters. Question 1. How much time does it take for the cannonball to hit the ground? Question 2. What is the horizontal distance the projectile travels before hitting the ground? Okay, so where is that? Here's the only marker I'm going to use. So, question 1, we'll write Q1 up here, wants to know how much time. So we'll put delta T here. And then question 2 wants to know the horizontal displacement. Okay, so let's do my favorite thing. I feel like that's way too close. Anyways, let's draw a picture. So here's the ground. They're on Mars. That's widespread. Actually, no, that would mess up gravity. They're not on Mars. They're on a golf course with red ground. That's why. Here's the cannon. And here's the cannonball. We'll draw motion lines because it makes things look animated. So then, when it starts off, it has the initial speed of 10 meters per second. Well, let's start our bank of knowledge. Bank of knowledge. It's gonna go like that. And then it's gonna end here. So, I guess I made that arc, oh well. I'll learn to deal. So its initial speed is 10 meters per second. Its initial height, oh, it was up in the air. So I guess this is just like a really, really large cannon. So we'll say that this right here is 45 meters. So, what should we call that? We'll call that delta y, because it's going to travel from this height of 45 meters here to 0 meters here, because it's going to land on the ground. So we'll just say that delta y is 45 meters. What else does it say? Oh, that's all the information it gives us. Well, from this, does it give us the angle? Is it fired at an angle? Oh no, it's horizontally. Oh, why am I doing projectile motion then? Oops, let me just change this real quick. Instead of looking like this big arc, because I thought that this was going to be fired at an angle, it's going to be fired purely horizontally. So I'll just erase that and I'll rewrite it. There's like a big red splotch everywhere now. So here's the cannon. And it's up 45 meters. And here's the cannonball, and it's just going to kind of go like that, and it's going to fall to the ground. Because it says that it is fired horizontally, so that means it doesn't have any vertical velocity. So, let's see. So we can say that that's its initial, and that's also its Vx, because in the x direction. Well, what's the best way to do this? What's the best way to explain this? I guess, maybe, I'm trying to find the best way to explain it, because in my notes I kind of go all over the place, and I don't know which way would be the quickest. Well, let's break up VI. So, we know when the cannonball starts out, it's going like this. So, its Vx is just going to be that. So then what's its Vy? It has none. So its Vy initial is equivalent to 0 meters per second. And its Vx is equivalent to 10 meters per second. So let me just erase that, get it out of the way. So then what else do we know? We know that it's in free fall. So its acceleration in the y direction is going to be negative 9.8 meters per second squared. What else do we know? We don't know delta x, so we'll put a question mark there. We don't know delta t. Those are what we're trying to find over there. I'm running out of room in my bank of knowledge. I probably should put this picture farther down. Oh well. And what else? We know, what else do we know? We know, I think we have everything we know. Okay, well now it's time to start using equations. So if we look at our kinematics equations, what we want, oh wait, we do know something. We know final velocity, do we? No, we don't. That's the one I forgot to put. I'm running out of room. I'll just put it here. Vy final also has a question mark. I knew I was missing one. Okay. So, now we have all these variables. And we'll use the y ones. So now I'm going to circle the y ones. I want to do it in different, I was about to do it in different colors, but I was like, oh wait, no, can't do that. So here are our y variables. And look, we have 3. 3 is the magic number, because once you have 3, you can use a constant acceleration equation. So what do we want to find? I think we're going to try to find, we'll try to find delta t, because that's what the first question asked for. So let's use our handy-dandy equations, and we'll use, how about, we have to look for the one that doesn't have final velocity, which is this one. Delta y is equivalent to initial vertical velocity times delta t plus, oh no, I'm running out of room, plus 1/2 acceleration in the y direction times delta t squared. Oh, okay. Well, I very much dislike this equation because you've got delta t squared and it just makes things a pain. So I like to solve for vyf first, just because I don't like dealing with square roots and all that stuff. If you want, you can solve it this way first, but I like to solve for vyf first and then use a different equation and plug in. So I'm just going to erase it and do it the way that I like it. Okay, so vyf. We're going to solve for vyf instead. So we've got vyf is equivalent to, vyf squared is equivalent to vyi squared plus 2ay delta y. Okay, let's plug in. Vyf, we don't know, so that's just going to be vyf squared is equivalent to vyi is 0, 0 squared is still 0, plus 2 times, oh, that's being all weird, negative 9.8 times 45. Okay, so did I seriously not bring my calculator down here? Wow, I am unprofessional, my goodness. I'll just do it on my phone, I guess, because wow, I'm really disappointed in myself. I thought I was more professional than this. My goodness. Yeah, oh well. Gotta turn it so I can get the big calculator. Negative 9.8, nope. Oh, I hate my phone calculator. Negative 9, negative 9, Okay, you know what? I'm just gonna pause this and go get my calculator. I will be back in like 2 seconds. I'll run, I'll sprint. I used to be a varsity sprinter. This is gonna be fast. Did I not? Oh, I didn't pause it. I wasn't all that fast. Oops. Okay, got it. Was that fast enough? I hope it was. Oh, wait. There we go. Okay, got it. So let's see. Now I'm out of breath from all that sprinting. 2 times negative 9.8 times 45 is equivalent to, here's my marker, is equivalent to negative 882. So vyf squared is equivalent to negative 882. And then take the square root of that, but we can't because it's a negative. So we're just going to erase the negative, because the thing with kinematics is with negatives, you can kind of just put them in where you know that you're going to need them. So if you just want to do everything in positive, and then you know that something has to be negative, like time we know isn't going to be negative, so we're going to make that positive. Displacement, no. So we can just kind of see, if that makes sense. I've been doing this for 40 minutes. Oh my god, no wonder why I'm out of breath. So square root of 882 is vy final is equivalent to 29.7. Okay, so now we're going to use another equation, the one that I like where we don't have to use delta t squared. So now we're going to use vyf is equivalent to vyi plus a delta t. Okay, so 29.7 is equivalent to 0 plus negative 9.8 times delta t. Then the 0 we can just ignore. I'll just erase that with my finger. Divide by negative 9.8 on both sides. Divide by negative 9.8. And what will we get? 9.7 divided by negative 9.8 is just about 3 seconds. And it comes out as a negative answer. You can just ignore that if you want. That's what I did, because I don't feel like dealing with it. So delta t is equivalent to 3 seconds. So I'm going to write that up here. Equivalent to 3 seconds. Well, now, I'll do this first and then I'll erase that. Well, now we know that the answer is narrowed down to between A or B, because those are the only ones that have 3 seconds for the answer to question 1. So now we have to find for B. Don't worry, B is going to be a lot quicker. This question is taking like 15 minutes now, something like that. Let me just erase all of this so we have room. Well, not all of it, but a lot of it. So now we get to use one of my favorite equations because it's so easy, the constant speed equation. I love it. It's great. Come on, there we go. I feel like by the end of this board is going to be pink. Where did I put my marker? Oh, here it is. Got it. Okay, so the constant speed equation, which is delta x is equivalent to vx times delta t. Well, guess what? We just found delta t, and we have vx. Where is it? There it is, 10 meters per second. So delta x is equivalent to 10 meters per second times 3 seconds. And guess what? That's gonna, I forgot the x. Wow. That's gonna equal 30 meters, and then we know that the answer has to be B. Because it says B, the answer to question 1 is 3 seconds, and the answer to question 2 is 30 meters. Good? Okay. Let's see. Oh, I have to plug in my computer or else it's gonna die on me. I was prepared for that though. I brought the charger. There we go. It's all better. Let's see. The one beneath that one. Wait, did I do the wrong question? Did I just spend all that time on the wrong question? Oh, I did. I'm sorry, Joe. I just did 17. Oh. So this one says, did I get this one wrong or right? I'm pretty sure I got this one right. Just gotta check on my test corrections. Oh no, I got this one right. Let me just erase this one. Oh, I'm sorry, Joe. I should really read the messages more often because that might save me a lot of stress. Because I keep like, oh no, this is a mess. By the time we do the finals live stream, well, it won't be the finals. It'll be the AP test review live stream. I'll be a lot better at this by then. Don't worry. I'm gonna be a lot better at this. The board is like slowly turning more and more pink as I use this red marker. This section over here especially, it's just all pink. Anyways. A stone of mass m is thrown vertically upward at an initial speed v(o) and reaches the maximum height h. At the same instant, another stone of mass m divided by 2 is thrown with the initial speed v(o) and an angle of 30 to the horizontal. The maximum height reached by the second stone would be, okay, so this one's a bit annoying. I circled it on my test because it was so hard. So let's see. So we have the first stone. We'll draw our picture smaller this time so I don't make the same mistake as last time. Can you actually see that side of the board? I'm not sure if you can. One sec, let me check something. Oh, and then after that, do the Angry Birds free response. Okay. I'm going to turn this a little bit so you can see that side of the board a bit better. Hopefully that worked. Okay. Anyways, so we're going to draw our first stone. There's one stone and it's thrown vertically upward and reaches the maximum height, h. So we're going to call this line right here h. We're going to call this line right here 0 meters because that's what it is. And it is thrown vertically upward and it reaches h. And then it's going to fall back down, but it doesn't say anything about that, so I guess we won't write that. At the same instant, another stone of mass m2 is thrown with initial speed of v(o) and an angle of 30 degrees to the horizontal. Then there's another stone that's thrown like this. Just pretend that's 30 degrees. And they both have the initial speed v(o). The maximum height reached by the second stone would be, okay, so for this we're trying to figure out delta y for the second stone. So we're going to write out our bank of knowledge. So delta y for the second stone is what we're trying to find, so we'll circle that. We have, well, here, we know that the initial speed is going to be v(o). We know that theta is equivalent to 30 degrees. So we need to find the vy of this equation. So let's look at the vector. So here it is, it's v(o) long, and it's at 30 degrees. What is the vx and the vy? Well, the vy is going to be equivalent to, let's see. Oh wait, I don't have real numbers. I don't have to do this with real numbers. Huh, okay, cool. Well, I'm going to go through this anyways because some people were confused about this, and this helped them a lot yesterday, so I'll do this anyways. So if we're trying to find this, we can look at this as a triangle. So we're going to erase this little line over here, and we're just going to move it over here, because that's the same here as there. The exact same distance. So now, we've got ourselves a 30, 60, 90. Cool. But I'll still use sine, cosine, theta. So that way, like, people can see how it works. So now from geometry, we know SOHCAHTOA. We know that sine is equal to opposite over hypotenuse. So the opposite of 30 is VY over the hypotenuse, which is VO. So sine of 30, not sim, sine of 30 is equivalent to VY over VO. Then VO times sine of 30 is equivalent to VY. And then you just do the same thing for the other one, except with cosine to get VX. But yeah, so hopefully that helps. That helped some people yesterday. So now we can write this as VYI is equivalent to VO sine of 30. Okay. Let's see. What else is there? So we've got, what do we have? Oh, we know the acceleration in the y direction is going to be AY is equivalent to negative 9.8. What else is there to know? We don't know the final velocity. We don't know delta t. Delta t is unknown. Vy final is unknown. What else do we know? Let's see. I'm trying to figure out where my work for this one starts and the other one ends, because it kind of blended all together. Oh, okay, well let's just assign some values, because I find assigning values helps a lot. Let's do, wait one sec, let me see. So if this is VO, oh okay, I see what I did. For this I said that VO was equivalent to 5 meters per second, so we're just going to write this up here. Then that would make Vx equivalent to 4.33 meters per second, and Vy equivalent to 2.5 meters per second. If you don't know how to do something with variables, just make up numbers and put them in. That's what I did. On the test, I just made up the number 5 for VO, and then I came up with these numbers right here. These right here. So, let's see. Then what did I do? So, we have the acceleration. Oh, I see what I did. That was pretty clever of me. Wow. Nice job, Sinead. So then we're going to do it like this. We know that VYF, well, I don't know why I came up with that. This is a strange problem. For whatever reason, I came up with VYF equals 0. I don't know why I thought that, but it worked. So I guess I shouldn't complain. But anyways, now we have this value, we have VYI, forgot the I. We have AY, so we need one more variable so that we can make an equation. So, what do we have? Oh, I completely forgot about the other stone. We can use the other stone, cool. Let's see, if it's thrown with the initial speed VO and reaches the maximum height H in this one, I'll just erase this to get it out of the way. I want to do another color, but I can't. So I'll just call this one stone A. And this one is stone B. So with the stone A bank of knowledge, we know, I don't feel like writing out bank of knowledge, so I'll just go BOK. We know that it's delta Y is equivalent to H. We know that it's VYI is equivalent to, we're going to say that this is 5 meters per second also because we came up with the idea that VO is equivalent to 5 meters per second. What else do we know about it? We know its acceleration. We know AY is equivalent to negative 9.8 meters per second squared. And we don't know delta T. That's unknown. And we don't know VYF. There we go. So, for some reason, I put VYF equals 0. I don't know why I did that, though. It's strange. I'll just show you what I did, and then if you remember how my mind works, let me know, because I have no idea why I did that, but it ended up working. So there must have been some reason, something that I knew then that I don't know now. My past self must have been smarter. So I'll just erase this, and then I'll show you what I did to get that. I want to erase my picture, though. I'll erase part of my face knowledge, though, because it's getting in the way. It's growing a lot. Sometimes on those projectile motion problems, it gets too big. I don't know why I put VYF equals 0, though. Let me see if someone in the comments knows. No. Oh, the Angry Birds free response. Did I do that in my first video? I might have done that before. I'll look at it. If it looks familiar, then I'll know. So anyways, VYF equals 0. Why did I stop? Why did you think that was 0? I honestly don't know. But delta y is unknown. That's what we're trying to solve. Acceleration, we'll just call it negative 10 meters per second to make it easier. And dyi is equivalent to, what did we solve it for? 2.5 meters per second. So now we're just going to solve for this. Oh, was I solving for, no. Oh, I see what I did. I was very clever. Wow. I was. Okay. Here's the difference. When I looked at this, I was really clever. Wow, I was a lot smarter in the past than I was. I looked at this. I didn't see this as going back down. I saw it as reaching its highest point. Okay. Because you know that when something reaches its peak, it stops. For just a second, it stops. So there, its final velocity is 0. Oh, okay. I knew my past self knew what I was doing. I was a lot smarter back then. So VYF is equivalent to 0 because it stops because we're only going to the peak because we're trying to find this. Okay. All right. That took a while to figure out, but we got there eventually. So VYI is equivalent to 2.5 meters per second. Why did I just erase that? I just had that there. Anyway, we're trying to find delta y. We don't know that. And we know that acceleration is equivalent to negative 10. So if we use our fancy kinematics equations, let's see, we're going to use, which one doesn't have t? This one. F to the second is equivalent to VI to the second plus 2AY delta y. Gotta put the y's there. So this is 0 is equivalent to, what's 2.5 to the second? 2.5 up to the second is 6.25 plus 2 times negative 10 is, well, I didn't need a calculator for that. Wow, Shani. Negative 20 delta y is equivalent to 0. So now we're just going to solve for this. So negative 6.25, if we subtract that, 20y. Because now I'm just subtracting this from both sides to get that along. And we're just going to divide by negative 20. Divide by negative 20. Negative 6.25 divided by negative 20 is equivalent to 0.1325 is equivalent to delta y for this stone. So this stone, delta y right here, is 0.3125 meters. So now, they write it in terms of h. So we have to find out what h is. How are we going to do that? We're going to see how high this thing went. So now we're going back to problem A. So here is A. I can't believe it took me so long to realize what I was doing in the past. Wow, that took way too long than I was supposed to. But anyway, so we know the initial velocity is 2.5. No, oops, sorry. I'm doing the one for the old problem. We know the initial velocity is equivalent to VO, which we decided would be 5 meters per second. We know that delta y is equivalent to h, which we're trying to figure out what that is. So I guess we'll do another question mark, we know that its final velocity is going to be 0 because it's going to stop at the top just for a minute, but it's still going to stop. We know that its acceleration is going to be negative 10 meters per second squared. And we've got our 3 magic variables. Oops, didn't we? Oh well. We've got 3 magic variables right here, so now we can use an equation to solve for them. And I'm running out of room, but I have just enough there. So now we can do, we need one without time. So we're going to use the same equation we used over here. Vyf up to the second is equivalent to Vyi up to the second plus 2ay delta y. When I write faster, it gets a lot messier. Anyway, 0 is equivalent to 25 minus 20 delta y. So we're just going to do the same thing we did over here, subtract 25 from both sides. And then equivalent to negative 20 delta y. Now we're going to divide by negative 20 on both sides. So negative 25 divided by negative 20 is equivalent to, I just want to check this. I get so paranoid that I'm going to make like some stupid little math mistake. And I'm paranoid for a good reason because I do it all the time. But I rely on my calculator so much. Is equivalent to 1.25 equivalent to delta y. So now what, we know that that is what h is. So what is 3.21 out of this? Okay. So there are options. Let's see. So if we do 0.3125 divided by 1.25, it ends up being, let's see, 0.3125 divided by 1.25 is not up to 315 divided by 1.25 is equivalent to 0.25, which is also equivalent to 1/4. So the answer is D, h divided by 4. That took a long time. And I've been doing this for an hour. Wow, my goodness. Does anyone know which number and which test the Angry Birds free response is? My guess is that, is it this one? Kinematics Chapter 3. Oh yeah, here it is. Oh no, never mind, those are spheres, not birds. Oh, the phone's ringing. One sec. No one I know, so I just hung up on them. There we go. I don't, yeah, if someone could tell me which one. Oh, no problem, Joe. Sorry that took so long. So if someone can tell me which test the Angry Birds free response is on, I'll do that. It's just slowly getting more and more pink. Let me see. I can look at my test. It might be 910. Oh no, this is like FBDs. Oh, which reminds me, Emily wanted me to do FBDs. Well, the second free response on the same test. Oh, okay, thanks again, Joe. Where did I put that? Over here. Free response number 2. Oh, okay. I'm actually pretty sure that I did this as my first video. So if you just go to my channel and you look at the first video, it's going to be there. So, yeah. Just go there. It'll be there. Emily, where are her questions? She emailed them to me, so I can do them. Oh, wait. Let's see. Okay, circular motion, graph symbols, variables. Okay, so let's go to our circular motion notes. Circular motion is pretty cool because things are pretty much the same as they were before. They just have different names, which, I mean, that's fine. It's like, I don't know, New York used to be New Amsterdam, then it changed. It's all cool. It's not too hard to remember. Let's see, where are my circular motion notes? Which kind of circular motion are we talking about? Do you mean rotational motion? I think you might mean rotational motion, but I'm not really sure. I'm just going to do rotational motion and then just tell me if I'm wrong, because I think that's what you mean. So we've we've got all these cool variables from before, where we have our, well, I guess we'll just call them one-dimensional motion variables. And we have got position, we have got displacement, we have got velocity, acceleration, force, and mass. These are our cool things from before. And we have a lot of cool equations with this, where we have like Newton's second law, and we have, they're used in kinematics a lot. Anyways, but then we have our rotational motion variables. Rotational motion. And these line up. I probably should have made this a chart and not like this. But anyways, I'll just draw lines. So this one is the same as, I forget what this one's called. Is this a theta? It might not be. Anyways, but it's like that. And then this one, delta theta. And these are called angular position and angular displacement. And then instead of velocity, we have this cool looking W thing. That's how I draw it. Sometimes I think that may be wrong the way I draw it, but it works for me. That's angular velocity. And then when we draw this, we have, I'm trying to like copy the picture with how they draw it, but mine just really ends up looking like an A. It's like this fancy looking A, and that's angular acceleration. And then instead of force, we have torque. Torque is really fancy. I can't draw this one, so I just kind of draw like a weird looking T. And then mass, we have inertial mass, which is just an I. Hopefully that helps. And like you can use the same equations with this. So like, you know how we find, I don't know, velocity is equivalent to displacement divided by change in time, right? Well, we can do the same thing over here with the same variable. So we know velocity, so angular velocity is equivalent to displacement, angular displacement, divided by, well, time is the same. Time is always the same. Divided by delta t over here. And so we can just do that, where we can just put things in. And it's the same thing for like acceleration is equivalent to change in velocity divided by change in time over here. Angular acceleration is equivalent to change in angular velocity divided by change in time. So it's really the same thing. I think that's pretty much everything. Does she have a lot more? Oh, FBDs. Some of the forces and review packet help. I don't want to be doing this for like 2 hours, because I feel like that might be a bit much. But I'll try and do some of this. Okay, so FBDs. Actually, can't use green. Never mind, forgot. So FBDs, I like them a lot, even if you just do them quick, because it gives you like a good picture of what's going on. So in FBDs, we have usually a dot in the middle, and then we have all the forces that are acting on the object. The dot represents the object. So like, we'll say that this is just resting on flat ground, and so there is a weight force pushing down, weight, which is also equivalent to its mass times its gravity. And then there's a normal force of the Earth pushing back up on it. So, well, normal, if it's like this, we know that the object is just sitting still on flat ground. It's not going anywhere. So we know that the normal and the weight force have to equal each other out, because this object isn't like falling through the floor. It's not flying through the sky. So the normal force and the weight have to equal out, so it's balanced in the y direction. Does that make sense? Good? Okay, so let's say that, let's say that we had a rope attached to this, and we are going to pull it this way, and it's on a frictionless surface. Is this going to move? Yes, it's going to move, because these two are going to cancel out. And it's got a net force going this way, so it's going to have acceleration, so it's going to move. Now let's say that it's on something with a lot of friction. it's on a very, very frictiony surface, and we're starting at rest, and we're pulling it, and it's not moving because there's this big static friction force on it. And it doesn't want to move. Which reminds me, do you guys know the difference between static and kinetic friction? I explained that the other day. I don't know. Let's see. He said rotational motion wouldn't be on the midterm. Oh, okay, cool. That's good. So then, in this case, the object isn't moving even though we're pulling on it because there's static friction pulling in the other direction, and these two cancel each other out, so there is no net force and there is no acceleration. If you need a reminder on what a net force is, a net force, I guess you could write it like that if you want, is the sum of all the forces acting on an object. So why do these cancel out? Because they're in the negative direction. So like the friction force is in the negative direction, the tension force is in the positive direction, and they're equal, they're going to cancel out. The weight is in the negative direction, the normal is in a positive direction, they're going to cancel out, turns into nothing. One of the cool things about static friction force, I don't want to confuse you on FBDs, so just kind of lock that in your head, and then I'll explain this cool thing. One of the cool things about static friction force is it's only as big as what's happening on the other side. Well, that's really true about any friction force. But, so like, say that I had a box sitting here, and I started pulling, well, I gotta draw the normal and the weight. Actually, this is gonna be the same drawing. I don't know why I didn't just use that one. But so I've got a tension force. The static friction force is only going to equal the tension force. It's never going to exceed it, or else it would start moving in the other direction, which would just be totally insane. Like if you started pulling on something and there was so much static friction that moved in the other direction, that's just absolutely impossible, so it never happened. So it's only going to equal this. And there comes a point where this is going to be where the static friction can't match it anymore, where it turns into kinetic friction. And kinetic friction is actually a little bit less than static friction, which people are like, wait, what, why? It's because, like, imagine you were pushing a really heavy bureau across a wooden floor. It's really hard to get that bureau moving, right? You have to push really, really hard to get it started. But then once you get it moving, it's a bit easier to push, right? Maybe you don't have experience pushing bureaus, but I do, and I can tell you that's true. Because the kinetic friction force is usually just a little bit smaller than the static friction force. Hopefully that makes sense. I might do maybe one or two more questions, and then I should probably go because I'm getting really hungry. Some of the forces by the equal 0, when to use this. Okay, when to use this. I feel like you can use FBDs whenever you really just want like a clearer picture of what's happening here, when you're like, okay, I don't really know what's going on right now, so I might as well just look and see what's happening, because it gives you a very clear picture of what's acting on the object. One thing that people sometimes get confused about is they write motion into these. They'll say like, oh yeah, say that there's just an object and it's not at rest. It's got a velocity going this way. They'll write in a velocity vector. They'll be like, oh yeah, it's got velocity, so it has to have a vector going that way. No, it doesn't. If it's moving at constant speed, it really doesn't. It can be moving, and you don't write a vector for movement, you just write vectors for forces. Hopefully that was helpful. It's been like an hour and 15 minutes. I think that's probably good. Text me if you have any more questions. I'll be in the school cafeteria at like, I don't know, probably around like 7 a.m. tomorrow morning if you want questions. If it's the second exam, then I'll help out in between the exams, but I think it's the first one, I'm pretty sure. But anyways, hopefully that was helpful. Thank you for watching. I gotta figure out how to stop this now. 1 sec. Oh look, here we go. Bye!